As we know, the greatest relative importance is found in chemistry, since it is and resides in everything, influences all sectors of life and our planet, and has a great objective to explain the change or internal processes of any material or phenomenon. For this reason, a very interesting and important topic related to inorganic chemistry is learning about unit cells, and our work team has carried out an investigation to show and develop in the following minutes the definition and characteristic structure to learn about this team. Welcome, and let's start. A unit cell is the smallest portion of a crystal lattice that shows the three-dimensional pattern of the entire crystal. A crystal can be thought of as the same unit cell, repeat over and over in three dimensions. The figure below illustrates the relationship of a unit cell to the entire crystal lattice. Let's talk about the relationship between unit cells and crystal structure. Crystals can be thought of as a repeating patterns, much like wallpaper or bathroom tiles, but in three dimensions. As we already know, the fundamental repeating unit of the crystal is called the unit cell, and it is a three-dimensional shape that can be repeated over and over by unit translations to fill space and leave minimal gaps in the structure. Some possible unit cells are shown in the title pattern at the right, along with arrows that indicate unit translation vectors. When considering the crystal structure of metals and alloys, it is not sufficient to think of each atom and its neighboring ligands as an isolated system. Instead, think of the entire metallic crystal as a network of atoms connected by a sea of shared valence electrons. The electrons are delocalized because there are not enough of them to fill each bond between atoms with an electron pair. For example, in the crystal structure of S block and P block metals, each atom has either 8 or 12 nearest neighbors, but the maximum number of S plus P electrons is 8. Thus, there are not enough to put two electrons between each pair of atoms. Transition metals can also use their d orbitals in bonding, but again, there are never enough electrons to completely fill all the bonds.
There are 7 existing crystal systems, but in this case we are going to see only 4, and they are simple cubic, body center cubic or BCC, face center cubic or FCC, and the last hexagonal closed package or HCP. The atoms in a metal lattice arrange themselves in a certain pattern which can be represented as a 3D box structure known as the unit cell, which repeat across the entire metal. The simple cubic unit cell is the simplest repeating unit in a simple cubic structure. Each corner of the unit cell is defined by a lattice point at which an atom, ion, or molecule can be found in the crystal. By convention, the edge of a unit cell always connect equivalent points. Some of the simple cubic features are the atoms in the primitive cubic unit cell are present only at the corners. Every atom at the corner is shared among 8 adjacent unit cells. 4 unit cells are present in the same layer. 4 unit cells in the upper lower layer. Therefore, a particular unit cell has the only 1/8 of an atom. Each small sphere In the following figure represents the center of the particle which occupies the particular position and not its size. The body-centered cubic, or BCC, is also called isometric, is one of the 7 existing crystal systems in crystallography. It is common in many minerals, such as pyrite or galena. Some BCC features. In BCC unit cell, every corner has atoms. There is one atom present at the center of the structure. According to this structure, atom at the body centers only belongs to the unit cell in which it is present. The face-centered cubic, or FCC, is one of the most stable crystal structures and has the highest packing density. In some textbooks, FCC may also be abbreviated as CCP, which stands for Cubic Closed Package. The face-centered cubic cell belongs to space group number 225, structure peerage A1, and Pearson symbol C4. Cu is the prototype for FCC. Some FCC features are: in FCC, unit cell atoms are present in all the corners of the crystal lattice. Also, there is an atom present at the center of every face of the cube. This face center atom is shared between 2 adjacent unit cells. Only 12 of each atoms belongs to a unit cell.
Hexagonal closed packet HCP. The hexagonal closed packet unit cell can be imagined as a hexagonal prism with an atom on each vertex and 3 atoms in the center. It can also be imagined as stacking 3 closed packets, hexagonal layers such that the top layer and bottom layer lay up. HCP is one of the most common structures for metals. HCP is one of the most stable crystal structures and has the highest packing density. Volume of a HCP unit cell. The volume of the hexagonal unit cell is the product of the area of the base and the height of the cell. For a closest packed structure, the atoms at the corners of base of the unit cell are in contact. A unit cell is the smallest representation of an entire crystal. The hexagonal closed packet HCP has a coordination number of 12 and contains 6 atoms per unit cell. The face-centered cubic FCC has a coordination number of 12 and contains 4 atoms per unit cell. Calculating numbers of atoms. To calculate the number of atoms is simple. Divide its weight in grams by the mu atomic mass from the periodic table, then multiply the result by Avogadro's number. The number of atoms that is included in the unit cell only includes the fractions of atoms inside of the box. Atoms on the corners of the unit cell count as 1/8 of an atom. Atoms on a face count as half. An atom in the center counts as a full atom. Simply cubic. A corner atoms multiplied by 1/8 is equal to 1 atom cell. The packing is the structure is not efficient, 52%, and so this structure type is very rare for metals. Body-centered cubic, BCC. A corner atoms multiplied by 1/8 plus 1 center atom multiplied by 1 is equal to 2 atom cell. The packing is more efficient, 68%, and the structure is a common one for alkali metals and early transition metals, allows such as brass, copper, zinc, also adopt these structures. Hexagonal close-packed HCP. Like the FCC structure, the packing density of HCP is 74%. Face-centered cubic FCC, Auscalic cubic close-packed CCP. A corner atoms multiplied by 1/8 plus 6 face atoms multiplied by a half is equal to 4 atom cell. This structure, along with its hexagonal relative, HCP, has the most efficient packing, 74%. Many metals adopt either the FCC or HCP structure.
Calculating the packing fraction. The packing fractions of the crystal structures shown above can be calculated by dividing the volume of the atoms in the cell by the volume of the cell itself. The volume of the atoms in the cell is equal to the number of the atoms slash cell times the volume of a sphere 4 slash 3 PR3. The volume of the cubic cells is found by copying the side length. Solved examples. Let's calculate the packing efficiency of a simple cubic unit cell. As we saw earlier in the section, a simple cubic unit cell contains an atom. The side length of the simple cubic unit cell is 2r, since the centers of each atoms occupy the corners of the unit cell, and the formula is questions. Lithium metal crystallizes in a body-centered cubic crystals. If the length of the side of the unit cells of lithium is 351 pm, the atomic radius of the lithium will be. And solution is.
Thank you for watching our video. We hope you enjoyed, and above all, that the knowledge has been extensive. Thank you very much, and see you later.